So the first one are filter methods, which are somehow model agnostic. Yeah, so we don't care about the actual learning model. Just look at the features, the feature spaces, the subspaces, and try to come up with some kind of measure, which is, as I said before, model agnostic. Yeah, so the basic idea is that we assign an importance score, or importance measure to each feature to filter out the useless ones. Yeah, so typically here we really look at individual features and sort out the potential irrelevant or redundant ones. Yeah? And examples for those measures here are information gain that you probably know from decision trees, entropy, of course, T-square statistics, TF-IDF for text could also be some kind of ranking here for those features. Yeah. It's model agnostic, meaning it's disconnected from the learning algorithm, so you can apply that for any kind of learning algorithm. On the other hand, that is a pro on the one hand. On the other hand, it's of course it's not accounting for a specific learning algorithm. So here are the pros and cons again. So first of all, it's fast and generic, model agnostic, and it's simple to apply. So you can do that in the pre-processing with different things here. Yeah. The con is it doesn't take into account interactions between features, because you typically only look at each feature individually and sort them out if they behave useless, so to say. Yeah. Yeah, individually irrelevant features we talked about that might be relevant together, but that would be missed in that case. Yeah. And once again, the question is that generic one maybe too generic because it's model agnostic, so maybe it's too generic in that case. Yeah. So generic could be a pro and a con in that case, so to say. Yeah. But once again, importance is measured on each feature individually, so we might miss the important features in the case that the features by themselves are irrelevant, but together they are highly relevant. Yeah? So that example from before. Then wrapper methods, where we try to somehow apply the whole thing, generate the candidates, and then apply the model, the learning model that we want to apply later on anyway, and see if the learning model actually performs good. If yes, then we keep that candidate. Yeah. If not, we look for the next candidate, so to say. Yeah. Or we test several candidates subspaces, of course, that can be done also. Yeah. So a learning algorithm is employed and its performance is used to determine the quality of the selected features. That obviously takes the dependencies into account, which is good. Yeah. So interactions between feature subsets, between the feature subset search, and the model selection, we have this interaction, which is beneficial, obviously. However, we have a higher risk of overfitting, because here, in general, if things are more generic, they are less overfitting. Yeah, so here the filter methods are extremely generic, not model specific. So the overfitting danger is minimized here. Here, we basically optimize for a learning model. That means that, of course, we may have a higher risk of overfitting. And of course, it's computationally more intensive, typically very intensive, because we have to build the classifier for all the candidates in order to find out which of the candidates are the best, or is the best actually. Yeah. So especially if the classifier, building the classifier comes with a high computational cost. Think about neural networks. In the worst case, well, you don't apply that for neural networks, of course, because neural networks will have would be a kind of embedded method here. Yeah, but think of some costly classifiers like a support vector machine or stuff like that, and you have to apply that for all the candidates that you actually generate in order to find out which one is the best. Yeah. So that is obviously a contra. Yeah, and the third one are the embedded methods, where we try to couple the whole thing, feature selection and learning together. So so to say, you you learn not only the outcome, but you also learn the important features for the outcome, like these deep neural networks, for example. And as I told you before, also the clustering algorithms typically try to the specific clustering algorithms for high dimensional data try to be embedded methods in terms of coupling of feature selection and clustering, so to say. So such methods integrate the feature selection in the model building. So decision tree is a good example. At each decision node, a feature has to be selected. So we somehow integrate the feature selection into the decision making, so to say. So that is a good example, decision tree, but also, of course, neural networks. Pro is, at least for the simple ones, less computationally intensive than the wrapper method. On the contrary, we have it is specific to a learning method. So that is the decision tree induction algorithm is only working for a decision tree, and gradient descent is only working for neural networks, so to say. I mean, not only, but especially working good or well for neural networks. So that is the downside, but it's somehow a kind of compromise between the wrapper methods and these standalone methods that we had before. Okay, so now let's have a look at the first step, actually. So that was the second step, evaluating the features. And now let's have a look at how to generate the candidate feature spaces. Sorry, how to evaluate the feature spaces that we come up with as candidates. And now let's see how we actually get the candidates, how we can generate the candidates. And there are many different ways or many different methods, general methods out there. Once again, the big problem is that we have such a huge search space. If we have n features, original features, we have 2 to the power of n possible candidates that we probably need to evaluate with one of those methods here. And that is much too many, of course. So with 20 features, we have already 2 to the power of 20 is always more than 1 million. That's a little bit too much, obviously. And very often we have, of course, much more than 20 features in our data set. So we need to come up with some heuristics to find the correct or to find good candidates, and there are many different ways to do that. So here's just an overview, and we will go through different things here. So forward selection is we start with an empty feature space and add relevant features. So that is a kind of bottom-up way, so to say. If you consider the same search space of frequent item set mining, you start with individual item sets and then try to add further item sets. So that's what actually a priori, for example, the a priori algorithm for finding frequent item sets is doing. So you start with basically an empty set and then add relevant features in that case. So that is bottom-up forward selection. Top-down backward selection is where you start with all the features and try to remove the worst ones, mostly the irrelevant ones. So that is top-down in the search space. And then you have things like branch and bound, where you try to find the optimal space under some monotonicity assumption, like a priori or FP growth or stuff like that. You could also, some methods also try to do that in a randomized way. So you just sample k-dimensional subspaces and work with them. So randomized search and so on and so on and so on. So there are many different other ways to do that, and we will have a look at these basic things here, these 4 things now in a little bit more details here.